Question 26F. The capture-recapture technique was used to estimate a population of seals in 2012. 60 seals were caught, tagged and released. Later, 120 seals were caught at random. 30 of these 120 seals had been tagged. The estimated population of seals in 2012 was 11% less than the estimated population for 2008. What was the estimated population for 2008? Now I'm going to use fractions to apply the capture-recapture technique. Let P represent the number of seals in the population, which is unknown at this point. So P over 60, and 60 is the number of seals that were caught, tagged and released, is equal to the number of seals that were caught the second time round, so this is the recapture part, over the number of seals of the 120 that were tagged. Now solving for P, so multiplying both sides by 60, P is equal to 60 multiplied by 120 over 30, which equals 240 seals. Now the estimated population of seals in 2012 was 11% less than the estimated population for 2008. So that means that, sort of going back in time, the population of seals would be higher. So we're expecting a value that's greater than 240. So let X represent the population of seals in 2008. And if we multiply that by 89%, which represents a reduction of 11%, so 100 minus 11 is equal to 89. So X times 89% is equal to 240. So after the reduction of 11% was applied, we have 240 seals. Let's reverse that by dividing 240 by 89%. So X equals 240 divided by 89%, which equals 269.66 and so on, and that rounds to 270 seals. Question 26G. Bawana purchases pool chlorine in a new container which holds 35 kilograms. She begins using this new container on the first day of a week. How many full weeks should this container last? Now the strategy here is to determine the number of cups used in a full week. Then from there, determine the mass of chlorine used in a full week, knowing that 1 cup is equal to 250 grams or 0.25 kilograms. And then from there, we can determine the number of full weeks that the container will last. So the number of cups in a full week, let's say the week starts on a Sunday, 3 cups used on Sunday, and then 1 cup per day thereafter. So for the remaining 6 days, 1 cup per day. So 3 plus 6 is equal to 9 cups per week. Now in terms of the mass of chlorine used, so 9 cups per week multiplied by 0.25 kilograms. So notice that I converted the grams into kilograms because the container or the pool chlorine is measured in kilograms. So I like to keep in the same unit of measure, of course. So 9 multiplied by 0.25 is 2.25 kilograms per week. And that's the amount of chlorine used each week or in a full week. So to determine the number of full weeks, the container is 35 kilograms when full, divided by 2.25 kilograms per week. And that gives us 15 5/9 of a week that this container will last. But the question's asking for how many full weeks should this container last? So the 15 here is 15 full weeks plus 5/9 of a week. So the solution is the container will last 15 full weeks. Question 27C. A map has a scale of 1 to 500,000. Part 1. 2 mountain peaks are 2 centimeters apart on the map. What is the actual distance between the 2 mountain peaks in kilometers? So if 1 centimeter corresponds to 500,000 centimeters in real life, then 2 centimeters, if we multiply that by 500,000, which is the scale, gives us the number of centimeters apart the 2 mountain peaks are in real life. Converting centimeters to meters, we divide by 100, and then converting meters to kilometers, we divide by 1,000. So 2 multiplied by 500,000 divided by 100 divided by 1,000 is equal to 10 kilometers. Part 2. 2 cities are 75 kilometers apart. How far apart are the 2 cities on the map in centimeters? So part 2 is just like part 1, but in reverse. So if 2 centimeters corresponds to 10 kilometers in reality, if we multiply the 10 kilometers by 7.5, we get 75 kilometers. To translate that back into a distance on the map, we need to multiply the 2 centimeters also by 7.5. So if 2 centimeters corresponds to 10 kilometers, then 2 times 7.5 centimeters corresponds to 10 times 7.5 kilometers in real life. So 15 centimetres corresponds to 75 kilometres in reality, so therefore the two cities on the map are 15 centimetres apart. Question 28C. Jacques and a flagpole both cast shadows on the ground. The difference between the lengths of their shadows is 3 metres. What is the value of D, the length of Jacques' shadow? Now the first thing to note here is that this triangle formed here by Jacques and his shadow and this dotted line is a scaled version of this larger triangle here. So this length here, the height of the flagpole and this dotted line. And the scale factor is 1.5 to 4. So we can form an equation. 1.5 to 4, so comparing the heights of these two triangles, is in the same ratio as the base lengths. So 1.5 to 4 is equal to D over D plus 3. Now we can solve for D. So cross multiply. 4 times D is equal to 1.5 multiplied by D plus 3. Expanding the brackets, we have 4D is equal to 1.5D plus 4.5. So 1.5D multiplied by 1.5 times 3 is equal to 4.5. Subtracting 1.5D from both sides, so collecting the like terms, we have 4D minus 1.5D is equal to 4.5. And 4D minus 1.5D is equal to 2.5D, and that equals 4.5. Dividing both sides by 2.5, we have D is equal to 4.5 over 2.5. And evaluating that fraction, we have D is equal to 1.8 metres. Question 17. Triangles ABC and DEF are similar. Which expression could be used to find the value of x? Now, since the two triangles are similar, that means that one triangle is an enlargement of the other. That also means that corresponding sides must be in the same ratio. So for example, DF over AC must equal DE over AB. And I've written that here. So side DE, so the hypotenuse of the larger triangle over the hypotenuse of the smaller triangle is equal to DF over AC. So they're the corresponding shorter sides. Now DF is 15 and AC of course is 10. And DE is X and AB is Y. Now we need to rearrange this equation and make X the subject of the formula. So multiplying both sides by Y, we have X equals Y multiplied by 15 over 10. And that means option C is the answer. Question 26D. A section of Jim's electricity bill is shown. Part 1. What is the value of A? Now the difference between the current reading and the previous reading gives us the energy used. So 531.2 minus 274.8 gives us 256.4 kilowatt hours. So in other words, A minus 560.9 equals 523.5. So let's reverse that. 523.5 plus 560.9 gives us the current reading of 1084.4 kilowatt hours. So part 2, how much will Jim save if he uses 154 kilowatt hours of energy at the off-peak rate rather than at the peak rate? So this is the peak energy charge or the peak rate here for peak time, and here's the off-peak energy charge there, 9.6 cents per kilowatt hour. So the difference between these two will give us the cost saving per kilowatt hour, and then we can multiply that by the number of kilowatt hours to give us the total cost saving. So 154 kilowatt hours multiplied by the peak energy charge minus the off-peak energy charge. So the difference between the two is the cost saving per kilowatt hour. Note that that's in cents, and that gives us 5,878.18 cents. Of course, we need to divide that by 100 to convert it into dollars. And Jim stands to save $58.78. Question 27A. Lucy went for a bike ride. She left home at 8 a.m. and arrived back at home at 6 p.m. A graph representing her journey is shown. Part 1. What was the total distance that she rode during the day? So what we look for is the point that's furthest away from the x-axis. So at this point here, Lucy's at home, so 0 kilometers from home, so she's at home. At 10 a.m., she's 20 kilometers from home. At 11:30, she's 30 kilometers from home. And at 12:30 p.m., she's 35 kilometers from home. And that represents the furthest distance away from home. But from this point, she then makes her way back home again. So the whole round trip is 35 kilometers plus 35 kilometers back home to give us a total of 70 kilometers. So part 2, how much time did Lucy spend riding her bike during the day? And from the travel graph, any horizontal section represents time that Lucy is not riding her bike. So from 8 a.m. to 6 p.m. we have 10 hours total, but the horizontal sections of the travel graph represent the time where Lucy is not riding her bike. So we have 1 hour plus another hour here, so that's 2 hours, plus 1.5 hours here, that's 3.5 hours. So 10 hours minus 3.5 hours gives us a total of 6.5 hours where Lucy has been riding her bike during the day. Question 30C. Joel mixes petrol and oil in the ratio 40:1 to make fuel for his leaf blower. Part 1. Joel pours 5 litres of petrol into an empty container to make fuel for his leaf blower. How much oil should he add to the petrol to ensure that the fuel is in the correct ratio? A very simple way to do this would be to take the 5 litres, divide it by 40, and then multiply it by 1 to give us the amount of oil required. But maybe before we do that, let's convert 5 litres into millilitres, since there's going to be a division involved. And by converting the litres into millilitres, hopefully we can avoid the use of decimals. So 5 litres is equal to 5,000 millilitres. Now to work out the amount of oil, 5,000 divided by 40, since 40 parts corresponds to 5 litres of petrol. So the value of 1 part is found by dividing it by 40, but then we multiply it by 1 because that corresponds to the second term of the ratio. So whatever this number is here, that corresponds to this number here. And that equals 125 millilitres of oil. Part 2. Joel has 4.1 litres of fuel left in his container after filling his leaf blower. He wishes to use this fuel in his lawnmower. However, his lawnmower requires the petrol and oil to be mixed in the ratio 25:1. How much oil should he add to the container so that the fuel is in the correct ratio for his lawnmower? There's many ways of going about this problem, but one way to think about it is, let's find out how much petrol there is left in the container. After all, there's petrol and oil mixed together to create this fuel. This is for the leaf blower. So the amount of petrol left in the container is found by taking how much fuel there is, which is 4,100 millilitres of fuel. So that's the petrol and the oil together. There are 41 parts in total, and that comes from the original ratio, 40:1. And then we multiply that by 40, since there's 40 parts petrol and 1 part oil. And that gives us 4,000 millilitres of petrol left in the container. Now remember that there's oil in the container as well. So if there's 4.1 litres of fuel, 4 litres or 4,000 millilitres is petrol, there must be 100 millilitres of oil in the container, which gives rise to this calculation. So oil left in the container is 4,100 millilitres, so that's the total amount of fuel, minus the amount of petrol that we just determined, and that gives us 100 millilitres of oil left. So now to determine how much extra oil to add. So oil needed for a 25:1 mix, we take the amount of petrol that we have in the container, divided by 25 multiplied by 1, so that comes from the ratio 25:1, and that equals 160 millilitres of oil. but we have 100 milliliters of oil already in the container. So only 60 milliliters extra oil needs to be added to then create a 25:1 petrol oil mix. Question 17. A child who weighs 14 kilograms needs to be given 15 milligrams of paracetamol for every 2 kilograms of body weight. Every 10 milliliters of a particular medicine contains 120 milligrams of paracetamol. What is the correct dosage of this medicine for the child? So now the first thing probably to note is the mass of the child is 14 kilograms. We know that we need 15 milligrams for every 2 kilograms of body weight. So 2 goes into 14 7 times. So the amount of paracetamol is going to be equal to 14 divided by 2. So that's the number of lots of 2 kilograms in 14. Multiply that by 15 milligrams. Okay, and we get, so 14 divided by 2 multiplied by 15, we get 105 milligrams of paracetamol. Now, we know that the rate of, or the rate of weight of paracetamol to the actual volume of the medicine is 120 milligrams to 10 mils. Okay, or we can say for every 10 milliliters, there's 120 milligrams of paracetamol. So why don't we do it in that direction then? So we know that 10 milliliters of the medicine contains 120 milligrams of paracetamol. Now, we can use the unitary method again to solve this, and we've used the unitary method in many other questions in the past. So once again, unitary method saves the day. So let's work out how many milliliters per 1 milligram of paracetamol. Okay, so 10 divided by 120 milligrams, so that gives us the milliliters per milligram. Multiply that by 105 milligrams, of course. Working that out quickly, we get 10 divided by 120 multiplied by 105, and we get 8.75 milliliters. So answer, option B. Question 18. The average New South Wales annual water consumption from the residential sector is equal to 90,340 litres per person per year. The Building Sustainability Index, BASICS, uses this as the benchmark to set a target for reducing water consumption by up to 40%. A new building planned to house 50 people has been designed to meet a 25% reduction on this water consumption benchmark. How much water per year to the nearest kilolitre is this building designed to save when fully occupied? Now, I think the first thing we need to work out is how much water 50 people are going to use in the year. So I'm just going to write down 90,340, and that's the consumption of water per person. So we need to multiply that by 50 because there's going to be 50 people in this building. Now, this 40% here is of little relevance in this question. So we just need to be mindful that not all the data given in the question is needed. What we do need though is this 25%. So this building is designed to save 25% on this target. So we're going to multiply that by 25%. Okay. And let's see what we get there. Okay, so 90,340 multiplied by 50 multiplied by 25. And we get 1129250. Now that's in litres. We need to convert that into kilolitres. So we divide that by 1,000 and we get 1129.25. And that's kilolitres. Okay, and the closest answer to that is option A. Question 20. In a household of 4, each member uses an average of 13 minutes of hot water per day. The household uses a 9 kilowatt hot water unit. Electricity is charged at 11.97 cents per kilowatt hour when the hot water unit is being used. What is the electricity cost for the hot water used by this household in 1 week? Now, the first thing we need to work out is the number of minutes a day this hot water unit is being used. So 4 people multiplied by 13 minutes per person gives us 52 minutes per day. Now the next thing we need to work out is the number of minutes per week. So 52 minutes per day, multiply that by 7 days in a week, we get 364 minutes in a week. The next thing we need to work out is the number of hours per week that translates to. So when we're working at electricity cost, the time must be in hours. So we take 364, we divide it by 60, and we get 6 1/15 of an hour per week. The next thing we need to work out is the energy consumed. That's in kilowatt hours. So we take the number of hours used, multiply that by the power rating of the unit itself. So 6 1/15 multiplied by 9, or 9 kilowatts, is equal to 54.6 kilowatt hours. The final thing we need to work out is the cost. So we take the energy used, so 54.6 kilowatt hours, multiplied by the cost of electricity in dollars per kilowatt hour. Notice that in the question, it's given in cents. So we need to convert that into dollars first. So that's 0.1197. Multiplying all that together, we get $6.54. So it's option B. Question 22. Heather's car uses fuel at the rate of 6.6 litres per 100 kilometres for long distance driving and 8.9 litres per 100 kilometres for short distance driving. She used the car to make a journey of 560 kilometres, which included 65 kilometres of short distance driving. Approximately how much fuel did Heather's car use on the journey? So the first thing we're going to do is we're going to split up the 560 kilometres into short distance driving and long distance driving. So I'll just say short distance is 65 kilometres. The long distance component is 560 minus 65, which is 495 kilometres. Okay, now to calculate the fuel consumption for both of these components. So the short distance fuel okay. Now, we're going to use the unitary method. So for short distance driving, it's 8.9 litres per 100 kilometres. So we're going to work out the fuel consumption per kilometre. So we're going to take 8.9 litres, we're going to divide it by 100, then we're going to multiply it by the actual kilometres travelled, which is 65 kilometres. And that's equal to 8.9. We're going to divide that by 100, and we're going to multiply that by 65, and we get 5.785 litres. Okay. Now, for long distance fuel consumption, okay, and long distance fuel consumption's less per 100 kilometres, so it's 6.6 divided by 100, so again using the unitary method, multiplied by the long distance kilometres, which is 495. Okay, so 6.6 divided by 100, multiply that by 495, and we get 32.67 litres. Now, if we add both of those numbers together, so 5.785 plus 32.67, we get, well, 38.455. So the closest answer will be B. That's correct to the nearest litre. Zuso is comparing the costs of two different ways of travelling to university. Zuso's motorcycle uses 1 litre of fuel for every 17 kilometres travelled. The cost of fuel is $1.67 per litre, and the distance from her home to the university car park is 34 kilometres. The cost of travelling by bus is $36.40 for 10 single trips. So which way of travelling is cheaper and by how much? And support your answer with calculations. So I think maybe we can start with travelling by bus. So why don't we work that out? Now, one single trip is going to be obviously a tenth of 36.40. So to go to university and back, so it's going to be 2 single trips. So what we can say is that one round trip, So a round trip is sort of back from home to uni, back home again, okay, is equal to 3640 divided by 10. So that gives you the cost of one single trip. We're going to multiply that by 2 to give us then the cost of a round trip. So home, uni, and back home again. So 3640 divided by 10. Okay, multiply that by 2 and we get $7.28. Okay, so now let's consider the motorcycle. Okay, so it's 34 kilometers. So this is from Zuso's home to university. So one round trip, let's work out the distance first, is equal to 2 times 34, okay, which is equal to 68 kilometers. Okay. So now let's work out how much fuel is actually used. So fuel used, okay. Now it's 1 litre for every 17 kilometres, and there's obviously 4 lots of 17 in 68, okay. But the way we can work it out, distance travelled, okay, divided by 17 will give us the number of litres. So that's going to equal 4 litres. So the cost is equal to 4 litres multiplied by the cost per litre, which is $1.67. Okay, so 4 times 1.67, and we get $6.68. Okay, so the motorcycle is definitely cheaper than the bus. And not that the question asks for it, but I'm going to work out what the difference is. So just to make it sort of more complete, $7.28 minus $6.68 by 60 cents. Thank you for watching. Question 28D. An aerial diagram of a swimming pool is shown. The swimming pool is a standard length of 50 metres, but is not in the shape of a rectangle. For part 1, by measuring the length AB, determine the scale of the diagram. So this is where you get a ruler and measure the length AB, and it's 8 centimetres. So the scale can be written as 8 centimetres equals 50 metres. But we need to simplify the scale by dividing both terms by 8. So 8 divided by 8 is 1 centimetre, and 50 divided by 8 is equal to 6.25 metres. So the scale can be written as 1 centimetre equals 6.25 metres. Now part 2, using this scale, calculate the length XY of the car park in metres. So again, we'll just measure this interval XY on the map, and that works out to be around 5.1 centimetres. And so using the scale, length XY on the map is 5.1 centimetres. Taking that length on the map and then multiplying it by the scale, 6.25, we get 31.875 metres. Question 26A. A farmer used the capture-recapture technique to estimate the number of chickens he had on his farm. He captured, tagged, and released 18 of the chickens. Later, he caught 26 chickens at random and found that 4 had been tagged. What is the estimate for the total number of chickens on this farm? So we could express this in the form of equivalent ratios. So we're trying to estimate a population of chickens, so let's call that population P. And of that population, the farmer tagged and then released 18 of them. Later on, okay, 26 chickens were caught, of which 4 had been tagged. Now we can express this in fraction form, and that certainly makes it easier to solve for P. So P over 18. So ratios and fractions are can be almost treated the same way, almost, is equal to 26 over 4. Multiplying both sides by 18, so moving this division by 18 over to the other side becomes multiplication. So P is equal to 26 over 4 multiplied by 18. Okay, and let's see what we get. So 26 over 4 multiplied by 18, and we get 117 chickens. Question 26G. Pat's mobile phone plan is shown. Last month, Pat made calls to the value of $561, sent 152 SMS messages, sent 37 MMS messages, and used 1.7 gigabytes of data. What was the total of Pat's phone bill for last month? So I think the first thing to note, looking at the bill, that Pat doesn't get charged for SMS or MMS messages. So really, we can just ignore these two lines. So it's really just the phone calls, okay? In fact, we've got that there to add as well, which is the monthly fee, the base fee for the mobile phone plan. So it's $49 per month, but we need to add on a little bit extra here. So pay any amount in excess of $550 for the calls, and we've got 561 here. So for the calls, okay, we have 561 minus 550, so that gives us $11 worth of calls that Pat will need to pay for. The other thing that we need to consider is the use of data. So let's work out how much data was used first. Okay, so usage is equal to, now we need to convert this into megabytes. So it's 1.7 gigabytes, and we multiply that by 1024. Okay, and okay, now that will give us 1740.8 megabytes. Yeah. Okay, so the excess usage is equal to 1740.8 minus 500 megabytes. Okay, so we'll subtract 500 from that, and we get 1240.8. Okay, so the data charge, okay, or the data cost, okay, is 1240.8, and it's going to be charged at $0.0293 per megabyte. 0.0293 to was it 9 to make sure I get this right? 293. Yeah. And we get $36.36 rounded to the nearest cent. Okay, so that's equal to $36.36. So the total phone bill, okay, is going to be equal to the standard monthly cost of $49 plus the calls, $11, plus the data cost, $36.36. Okay, adding all that together, so 49 plus 11 plus $36.36, we get $96.36. Question 27A. At a particular time during the day, a tower of height 19.2 meters casts a shadow. At the same time, a person who is 1.65 meters tall casts a shadow 5 meters long. What is the length of the shadow cast by the tower at this time? So this is a question that's based around similar triangles, and I want you to notice here we have the large right angle triangle, okay, and that is similar to the small right angle triangle. What that means is that the corresponding sides are all in the same ratio. But it also means that sides relative to each other are also in the same ratio. So in other words, 1.65 to 5, so let's write this ratio down, 1.65 to 5, and I'll write it as a ratio, so using the correct notation, is equal to 19.2 to this sort of the length of the shadow. So 19.2, let's call it x. Okay, so let's call that the length of the shadow x. So let's solve this. 1.65, we will solve it by treating the ratio as a fraction. 1.65 over 5 is equal to 19.2 over x. Now, the x is in the denominator. When you're trying to solve for a pronumeral, it's nice to have that in the numerator. So we can, in fact, we could flip both these fractions. So why don't we do that? So in other words, 5 over 1.65 is equal to x over 19.2. What you do to one side, you do to the other. Okay, so if you invert both fractions, you haven't changed the integrity of the equation. I mean, the left-hand side still equals right-hand side. Now let's make x the subject of the formula. We're going to move the 19.2 over to the other side. So let's do that. So 19.2 multiplied by 5 over 1.65 is equal to x. So let's evaluate the left-hand side. I'll just brighten the display a little bit there. Okay, so 19.2 multiplied by 5 over 1.65, and we get 58.18. So okay, and let's see if there's any rounding required. No rounding required, so we could leave it to correct to 2 decimal places. Question 27b. A patient requires 2,400 milliliters of fluid to be delivered at a constant rate by means of a drip over 12 hours. Each milliliter of fluid is equivalent to 15 drops. How many drops per minute need to be delivered? So let's work out the number of drops or number of drips in total. We have 2,400 milliliters, of which each milliliter is 15 drops, or is equivalent to 15 drops. So the number of drops, okay, in total is equal to 2,400 milliliters. So that's the total amount of fluid to be delivered, multiplied by 15, and that equals, okay, so 2,400 multiplied by 15, we have 36,000 drops. So, and that's over a 12-hour period. Okay, so we have 36,000 drops. So we'll express this as a rate per 12 hours. But we need this per minute. So let's divide everything by 12, both terms by 12 to get it per hour. Okay. So 36,000, divide that by 12, so we get the number of drops per hour needed, which is 3,000. Per hour. Now let's divide both sides by 60 to express the rate in drops per minute. So 3,000 divided by 60, and we get 50 drops per minute. Question 29c. The image shows a rectangular farm shed with a flat roof. The width of the shed indicated by the dotted line was measured using an online ruler tool and found to be approximately 12 meters. Part 1. By measurement and calculation, show that the area of the roof of the shed is approximately 216 square meters. So we need to come up with a scale first of all. So we're told that the diagram is to scale, the photograph is to scale. Okay, so we can see there that 40 millimeters corresponds to 12 meters in reality. Okay, so let's write the scale there. In fact, in fact, I'll do it as an arrow there. So scale is equal to 12 meters. So that's the width of the shed. So let's work out the length based on that scale. Okay, so we can see there that the length of the shed is 60 millimeters. Okay, is 60 millimeters, but we divide it by 40 millimeters, then multiply it by 12. So this is the unitary method. Okay, and then we multiply that by 12, and that gives us then the real life length of the shed. So 60 divided by 40, and we're going to multiply that by 12, and we get 18, so that's 18 meters. Okay, so area is equal to 12 multiplied by 18. Okay, so therefore, so 12 times 18, and we get 216. As required. Okay. Part 2. All the rain that falls onto this roof is diverted into a cylindrical water tank which has a diameter of 3.6 meters. During a storm, 5 millimeters of rain falls onto the roof. Calculate the increase in the depth of water in the tank due to the rain that falls onto the roof during the storm. So the first thing we need to do is to work out the volume of water that's fallen. So we're going to work that out in cubic meters. Okay, so volume is equal to AH. Okay. And we have our A is equal to 216. So that's what we worked out previously. In fact, we're given that anyway, even if you couldn't work out part 1. And our H, okay, is the depth of rain, which is 5 millimeters, but we need to convert that into meters. So that's going to be, okay, so 5 divided by 1,000, so that's converting millimeters into meters. Okay, so 5 divided by 1,000, and we get 0.005. Okay, so therefore the volume of rain is equal to 216 multiplied by 0.005, and that gives us 216 multiplied by 0.005, and we get 1.08 cubic meters. Or that's 1.08 kiloliters, or 1,080 liters of water. So for the next part, this amount of water, so just over a cubic meter, is going to be diverted into a cylindrical water tank. Okay, so, and the diameter of the water tank is 3.6 meters, which means immediately we need to convert that into radius. So we're going to divide that by 2, and we're going to use basically the same formula again. Volume equals AH, but this time instead of a rectangular prism, okay, we're going to be dealing with a cylinder instead. So that's going to be pi r squared times h. Okay, so volume of cylinder. Okay, so that's going to be V is equal to pi r square h. Now, we have the volume already. Now, this is not the volume of the entire cylinder. This is just the volume of water in the cylinder. So I couldn't fit that there. So volume, we got 1.08. Okay, so 1.08 is equal to pi multiplied by r squared. So if the diameter is 3.6, the radius is 1.8. Okay, squared multiplied by h. And we're going to make h the subject of the formula. So h is equal to 1.08 divided by pi divided by 1.8 squared. And we'll enter that expression into the calculator and see what we get. Okay, so 1.08, we're going to divide that by pi, and we're going to divide that again by 1.8 squared. And we get 0.1061. Okay. And sometimes it helps just to go back over the question quickly. It says calculate the increase in the depth of water in the tank due to the rain that falls. It doesn't actually say to round it, but 2 decimal places is fine. I'm going to quote it in meters and also in centimeters as well. So that's approximately 10.61 centimeters. Question 30A. The energy consumption of a computer in standby mode is 21 watts. The cost of electricity is 31 cents per kilowatt hour. A school computer room has 20 computers. How much will the school save by switching off all 20 computers during the 11 weeks of school holidays? So going back now, just looking at various bits of data in the question. The first one is each computer draws 21 watts. We work in kilowatts when we're dealing with energy consumption and energy cost. Also, the cost is in dollars, not in cents. So there's just 2 things to be mindful of here. And we have 20 computers. So let's calculate the energy consumed. And that's also over the 11 weeks of school holidays. So we need to work out, basically, it's kilowatt hours. So we need to work out total number of hours over the 11 weeks. So energy consumed is equal to, we've got 21 watts, but we need that in kilowatts. So let's divide that by 1,000. Okay, so that's 21 watts divided by 1,000, converts it into kilowatts. Now we have 20 computers. So there's the times 20 there. Okay, and that's for 24 hours a day times 7 days per week times 11 weeks. So calculating that, or just evaluating that on the calculator. Let me just brighten the display just a little bit there. Okay, so 21 watts divided by 1,000, converting that into kilowatts. Multiply that by the total number of hours. So there's 20 computers, and they're on standby for 24 hours a day, 7 days a week for 11 weeks. And we have 776.16 kilowatts. Okay, actually kilowatt hours, sorry. We just need to convert that into an actual cost though. So the actual energy cost, okay, is the energy consumed, 776.16 kilowatt hours, and then multiply it by the cost per kilowatt hour, which is 31 cents, or in dollars, 0.31. Okay, so we can take our last answer, so just multiply by 0.31, and we have $240.61 saved. Question 9. An old washing machine uses 130 litres of water per load. A new washing machine uses 50 litres of water per load. How much water is saved each year if 2 loads of washing are done each week using the new machine? So first of all, let's work out the saving per load. Is equal to the amount of water used in using the old washing machine, which is 130 litres, minus the amount of water used in the new washing machine, which is 50. 130 minus 50 is equal to 80 litres saved per load. Now, Each week there are 2 loads of washing, so let's see how many loads of washing we're doing a week. So there's 2 loads of washing per week. There are 52 weeks in a year, so we'll just keep it nice and simple, not 52.18. And each load we're going to save 80 litres of water. So let's multiply all those together and see what we get. 2 times 52 times 80 litres, and we get 8,320 litres. Option D. Question 11. The concentration of a drug in a certain medication is 100 milligrams per 5 millilitres. A patient is prescribed 2,000 milligrams of the drug. How much medication should be given to the patient? So what we're going to do is we're going to write this rate back to front. You'll see why shortly. So we're going to write it as 5 millilitres per 1,000 milligrams of the drug. And we're going to use the unitary method then to calculate the number of millilitres. So in questions involving rates, it helps to write the unknown or the thing that you're trying to find, which is the number of millilitres, as the first term. So the way we're going to work it out is we're going to use unitary method per milligram. So 5 millilitres divided by 100 multiplied by 2,000, since that's the amount of the drug that's being administered, and multiplying all that together. Let's see what we get. So 5 divided by 100 multiplied by 2,000, and we get 100 millilitres. So answer C. Question 15. Calls on a mobile phone plan are charged at the rate of 54 cents per 30 seconds or part thereof. What is the cost of a call lasting 2 minutes and 15 seconds? So I think the key word here is part thereof. So we just need to find how many 30-second blocks or even part of a 30-second block there are in 2 minutes and 15 seconds. So 2 minutes has 4 such blocks, and then we go over the 2 minute mark, which means that we're going into the next 30-second block, but it only takes up 15 seconds. So that means that there are 5 30-second blocks. So the answer is 5 times 54 cents. So I'm going to write it in dollars. Okay. And that's going to be, if you get a calculator, of course, right. Then when you're under exam pressure, don't do this mentally, just work it out with your calculator and you get $2.70. So option D. Question 16. The width W of a river can be calculated using 2 similar triangles as shown in the diagram. What is the approximate width of the river? Now, the 2 triangles are similar, which means that the ratio of the corresponding sides must be similar. So we could write it this way. W over 20.3 must equal the ratio of the 2 corresponding sides. So the side that corresponds to W is 7.1 over 8.1, which corresponds to the 20.3. Now, to solve for W, we just multiply the fraction on the right-hand side by 20.3. So W is equal to 7.1 over 8.1 multiplied by 20.3. Okay, let's get our calculator. Have that ready. So 7.1 over 8.1. Just put it in the right mode first. 7.1 over 8.1 multiplied by 20.3, and we get 17.793. And that's option A. Question 26C. Peter's car uses fuel at the rate of 5.9 litres per 100 kilometres for country driving and 7.3 litres per 100 kilometres for city driving. On a trip, she drives 170 kilometres in the country and 25 kilometres in the city. Calculate the amount of fuel she used on this trip. So we're going to use the unitary method to solve this. So let's have a look at the country driving first. Okay. And what we want to work out is the number of litres used per kilometre and then multiply it by 170. So that's going to be 5.9. We're going to divide that by 100. and then we're going to multiply that by 170. Okay, so 5.9 divided by 100 multiplied by 170, and we get 10.03 litres. Now let's have a look at the city fuel consumption. Okay, so it's 7.3 litres per 100 kilometres. Let's work it out per kilometre, and we're going to multiply that by 25 to work out the number of the litres used in the city. So 7.3, divide that by 100, multiplied by 25, and we get 1.825. 1.825 litres. Add the two together. Total used is equal to 10.03 plus 1.825, okay, plus 10.03, and we get 11.855 litres. Question 28a. Jacob has a large jar of silver coins. He adds 20 gold coins into the jar. He then seals the jar and shakes it to ensure that the gold coins are mixed in thoroughly with the silver coins. Jacob then opens the jar and takes a handful of coins. In his hand, he has 33 silver coins and 4 gold coins. Part 1. Based on Jacob's handful, if a coin is selected at random from the jar, what is the probability that it is a gold coin? So in his hand, how many coins does he have? He's got 33 silver coins plus 4 gold coins, so there's 37 coins, of which 4 are gold. So the probability is 4 over 37. In part 2, Jacob returns the handful of coins to the jar. Estimate the total number of coins in the jar. So we're trying to estimate the silver coins. So a good tactic would be to maybe make the silver coins, in terms of expressing this as a ratio of silver to gold. Since the silvers are unknown, let's make the first term of the ratio unknown and give it a pronumeral, say x. And he's added 20 coins. So silver coins to gold coins, and there's 20 gold coins in the jar, is equal to 33 silver coins to 4 gold coins. So this was the sample. So this is a capture recapture method, and the recapture had, well, Jacob had 37 coins, 33 were silver, 4 were gold, and we're assuming everything was completely random and thoroughly mixed, as the question does say, that the ratio x to 20 should be equivalent to the ratio 33 to 4. So let's solve it. In fact, we could treat this as a fraction. X over 20 is equal to 33 over 4. So x is equal to 20 multiplied by 33 over 4, which equals 20 multiplied by 33 over 4, and we get 165 silver coins. So the total number of coins, we need to add the gold coins as well. Okay, is equal to 165 plus 20, which is 185 coins in total. Question 28b. The cost of buying a new heater is $990. It uses energy according to the following energy label. Energy is charged at the rate of 35 cents per kilowatt hour. How much will it cost in total to purchase and then run this heater for 5 years? So there's two elements here, there's two components to this cost. We have the purchase cost, and we also have the running cost based on the number of kilowatt hours per year, and it uses 505 kilowatt hours per year at this following rate, 35 cents per kilowatt hour. So we can do this on one line, so $990 plus, let's work out the total amount of energy used in 5 years, so that's 505 kilowatt hours per year, multiplied by 5 years, multiplied by the cost, or the energy cost per kilowatt hour, 0.35. And just entering all that into the calculator. So this expression, 505 multiplied by 5 multiplied by 0.35. And we get $1,873. $1,873.75. Question 30A. The area of a roof is 30 square meters. Any rain that falls on the roof flows directly onto a garden. Calculate how many liters of water flow onto the garden when 20 millimeters of rain falls on the roof. So all we need to do is just really convert the 20 millimeters into meters, multiply it by the area of the roof, we get the volume in cubic meters, and then we convert that into liters. So volume is equal to AH, okay, area of the base times the height. So we kind of sort of imagine, okay, some sort of a rectangular prism, okay, something like that, and you know, it's sort of 20 millimeters high, that's how much rain falls, and the area of the base of this prism is 30 square meters. Okay, and it's just sort of filling up with water. Okay, so volume is equal to the area of the base, which is 30 square meters, multiplied by the height. Now the height must be in meters, so 20 millimeters, converting that into meters, so hopefully we know our conversions. We'll divide that by 1,000. And let's see what we get. Okay, so 30 multiplied by 20 millimeters, and we're going to divide that by 1,000, of course. We need that in meters, and we get 0.6 cubic meters. And that is in fact equal to 0.6 kiloliters. So 0.6 kiloliters, we're going to convert that into liters. We multiply that by 1,000, and we get 600 liters of water. Question 14. Kate is comparing two different models of car. Car A uses fuel at the rate of 9 litres per 100 kilometres. Car B uses 3.5 litres per 100 kilometres. Suppose Kate plans on driving 8,000 kilometres in the next year. How much less fuel will she use driving car B instead of car A? So what we need to do is work out how many litres of fuel the car's going to use over 8,000 kilometres. So we're going to use the unitary method here. So let's have a look at car A first. So let's work it out as in terms of the amount of fuel per kilometre. So 9 litres divided by 100 kilometres, but then we're going to multiply it by 8,000. And that gives us the amount of fuel that car A is going to use over 8,000 kilometres. So let's work that out quickly. 9 divided by 100 multiplied by 8,000, and we get 720 litres of fuel. Okay, so this is for car A. What about car B? We're going to do the same thing as well. So 3.5 divided by 100 multiplied by 8,000. Okay, and we'd expect a significant difference here actually. So 3.5 divided by 100 multiplied by 8,000, and we get 280 litres of fuel. So the answer is the difference between those two numbers. So 720 minus 280, we get 440 litres, option B. Question 16. The benchmark for annual greenhouse gas emissions from the residential sector is 3,292 kilograms of carbon dioxide per person per year. A new building planned to house 6 people has been designed to achieve a 25% reduction on this benchmark. What is the maximum amount of carbon dioxide per year to the nearest kilogram that this building is designed to emit when fully occupied? So we know that there's 3,292 kilograms of carbon dioxide emitted per person. Okay, so there are 6 people and there's this much carbon dioxide. So let's multiply those two together. 6 people, each one emitting 3,292 kilograms per year. But there's going to be a 25% reduction as well. So there's only 3 things we have to consider here. So reducing that by 25%, we could multiply that, bit of a shortcut here, by 75%, because that's when you take off 25%, you have 75% remaining. Let's multiply all that together. 6 times 3,292 multiplied by 75%. Okay, and we get 14,814. Okay, so it's going to be option D. Question 26A. Electricity costs 27 cents per kilowatt hour. How much does 20 kilowatt hours cost? So we take the cost per kilowatt hour, which is 27 cents, multiply it by 20, and we get $5.40. Question 26B. Toby's mobile phone plan costs $20 per month, plus the cost of all calls. Calls are charged at the rate of 70 cents per 30 seconds or part thereof. There is also a call connection fee of 50 cents per call. Here is a record of all his calls in July. How much is Toby's mobile phone bill for July? So first of all, Toby has to pay $20 per month regardless. So let's start with that. Secondly, he's made 3 phone calls in July, and each phone call has a 50-cent connection fee. So we've got 3 lots of 50 cents. Now let's analyze each of the calls. So his first call is a 20-second call, which falls within the first block of 30 seconds. So there's going to be 70 cents for that call. The second call on the 12th of July is 40 seconds, so that takes up 1 block of 30 seconds plus a little bit of the next block of 30 seconds. So there's 2 lots of 70-cent blocks that are used. Finally, the 23rd of July, okay, we have a 2-minute 15-second phone call. 2 minutes, that's 4 blocks of 30 seconds. Okay, so each minute is 2 lots of 30 seconds. So there's 4 lots of 30 seconds plus 15 seconds, that makes it 5 lots of 30-second blocks. And each 30-second block is worth 70 cents. And all we've got to do now is just add that all up. Okay, so let's do that. 20 plus 3 lots of 50 cents plus 70 cents for the first call plus 2 lots of 70 cents for the second call plus 5 lots of 70 cents for the third call. And that gives us a grand total of $27.10. Question 26C. A farmer needed to estimate the number of goats on his property. He tagged 80 of his goats. Later, he collected a random sample of 45 goats and found that 16 of these had tags. Estimate the number of goats the farmer has on his property. So let's write this as a ratio first. So we have 80 tagged goats to some unknown number is equal to the ratio of the tagged goats to the total number of goats in the sample. So in the sample of 45 goats, 16 were tagged. So that's going to be 16 to 45. Okay. Now what we can do is we can express it as 2 equivalent fractions, in fact. So we could write it as x over 80. Okay, so second term over the first term is equal to 45 over 16. Now let's solve for x. X is equal to, we can move the 80 over, multiply the 80 by the fraction 45 over 16. Okay, we can evaluate this expression now. So 80 multiplied by 45 over 16, and we get 225. Therefore, estimated number of goats equals 225. Question 5. The driving distance from Alex's home to his work is 20 kilometers. He drives to and from work 5 times each week. His car uses fuel at the rate of 8 liters per 100 kilometers. How much fuel does he use driving to and from work each week? So each day, Alex is going to be driving 40 kilometers. 20 kilometers to work, 20 kilometers back home. So it's going to be 40 kilometers per day, 5 times each week. So that's going to be 200 kilometers. His car uses fuel at the rate of 8 liters per 100 kilometers. We have 200 kilometers here, so this implies it's going to be 2 times 8 liters, which is 16 liters of fuel for the week. Option A. Question 10. A biologist caught a random sample of 56 parrots in a national park. She tagged them and then released them. She later returned to the park and caught a random sample of 47 parrots. In this sample, 29 had been tagged. Using the capture-recapture technique, what is the estimated number of parrots in the park? Let's have a look at the recapture first. We have 47 parrots captured, of which 29 have been tagged. So we're going to write this as the ratio 29 to 47. In the original capture, 56 parrots were tagged, so that corresponds to the 29, to a total number of parrots in the forest, which we don't know, which we're going to use the pronumeral x to represent. We're going to write this now as a fraction. So 47 over 29 is equal to x over 56. So it's the second term over the first term in each respective ratio. Let's make x the subject of the formula. So we're going to multiply the fraction 47 on 29 by 56. So 56 multiplied by 47 over 29, and that's equal to x. Okay, so 56 multiplied by 47 over 29, and just press the SD button, we get 90.758. And that's going to be closest to 91. So it's going to be option C. 26G. A field diagram of a block of land has been drawn to scale. The shaded region ABFG is covered in grass. The actual length of AG is 24 meters. Part 1. Show that the scale of the diagram is 1 centimeter equals 3 meters. So the first thing that we need to do is to measure the length of AG on the diagram, and it happens to be 8 centimeters. So let's just write that down. So is equal to 8 centimeters. Right. Hence the scale is 8 centimeters is equal to 24 meters in reality. Now, dividing both sides by 8, is 1 centimeter equals 3 meters. Let's have a look at part 2. So part 2 is on a new page. So question 26, part 2. How much fertilizer would be needed to fertilize the grassed area ABFG at the rate of 26.5 grams per square meter? So what we'll need to do is to calculate the area of this shape. And this shape's in fact a trapezium, or you could calculate it as a rectangle plus a triangle. So what we'll need to do is to use our scale. Okay, so this is the scale. 1 centimeter is equal to 3 meters. Okay. So what we do is that we measure the number of centimeters of each of the edges, okay, each of these intervals, and then multiply by 3, and that's the answer, or the length of that interval in meters. So that's 3 centimeters there. Multiplying it by 3 this is going to be 9 meters. Okay. AE, actually, we'll treat it as a trapezium. Okay. So we know that's 8 centimeters already. We know that's 24. So I'm just going to write 24 there. Okay. We'll need BF, and that's 6 centimeters. Multiplying that by 3, we get 18. And that's all. So let's work out the area now. So area of ABFG is equal to, now I'll turn this around so you can see that, the average or the mean of the parallel sides of this trapezium. So it's 18 plus 24 on 2. Multiplied by the distance between the parallel sides, or the height, which is 9 meters. Okay, so just entering that in. 18 plus 24 over 2 multiplied by 9, and we get 189 square meters. So how much fertilizer then would be needed? So it's equal to 189 square meters multiplied by the rate, which is 26.5 grams per square meter. And we get 5,008.5 grams. Or that would be 5.0085 kilograms, but this answer here would be sufficient. Question 27A. Jenny used her mobile phone while she was overseas for 1 month. Her mobile phone plan has a base monthly cost of $50. While overseas, she also charged 33 cents per SMS message sent and 26 cents per megabyte of data used. During her month overseas, Jenny sent 120 SMS messages and used 1,400 megabytes of data. What was her mobile phone bill for the month overseas? So first of all, her base monthly cost was $50. Now, she was charged 33 cents per SMS, so that's 0.33, and she sent 120 SMSs. The cost per megabyte of data used is 26 cents per megabyte, and she used 1,400 megabytes. So entering in all of that into the calculator. So 50 plus 0.33 multiplied by 120 plus 0.26 multiplied by 1,400, and we get $453 and 60 cents, and that was her bill for the month overseas. Question 28C. Every day, a 1,200 watt microwave oven is used for 45 minutes at 40% power. Electricity is charged at 25 cents per kilowatt hours. What is the cost of running this microwave oven for 180 days? So I think the first thing we need to do is to work out the power consumption first, then we'll work out the energy consumption in kilowatt hours, then we'll work out the cost per day, and then we'll multiply that by 180 days to get total cost for those 180 days. So power, okay, is equal to 1,200 watts. Now we need this in kilowatts, so we need to divide this by 1,000 to convert that into kilowatts, because all calculations must be in kilowatts to work out the cost. And it's also running at 40% power, so we're going to multiply this by 40% as well. So working that out, 1,200 watts, converting that into kilowatts by dividing it by 1,000, and then multiplying it by 40% because we're running the microwave at 40% power, and we have 0.48 kilowatts. Now let's work out the energy used. So energy is a product, okay? So it's the product of power and time, but the time must be in hours. So energy used is equal to the power, so 0.48 kilowatts. And we're going to multiply that by the number of hours used per day. And that's going to be 45 minutes. So converting 45 minutes into hours, we need to divide that by 60. Okay, and we get 0.48 multiplied by 45 over 60, and we get 0.36 kilowatt hours. So energy is in kilowatt hours, 0.36 kilowatt hours, and that's per day. So let's just clarify this to make sure that we remember to multiply this by 180 days in the end. Okay, so let's work out the cost per day. Okay, is equal to 0.36 kilowatt hours. We're going to multiply that by the cost per kilowatt hour, so it's $0.25. Okay, so 0.36 multiplied by 0.25, and we get 9 cents. That's per day. And finally, the cost for 180 days. Okay, is equal to the cost per day, 0.09. Multiplying that by 180 days. Okay, so 0.09 multiplied by 180 days, and we get $16.20. Question 2. Sugar is sold in 4 different size packets. Which is the best buy? So the way to answer this question would be to maybe look at a common mass. So for example, the cost per kilogram would be something to compare against, and then compare the cost per kilogram for each of the options. So for 100 grams, it's 40 cents. Okay, so if we multiply that by 10, okay, because there's 10 lots of 100 grams in a kilogram, we end up with 1 kilograms is equal to $4 for this option. Okay, now clearly we have 1 kilograms for $3.50, so we can't be option A. Okay, what about option B? 500 grams for $1.65. So if we multiply that by 2, because there's 2 lots of 500 grams in a kilogram, 2 times $1.65 is $3.30. So 1 kilogram is equal to $3.30. So clearly it's cheaper than option C. So far it's between option B and option D. Now, option D, if we halve that one there, okay, $2 kilograms becomes 1 kilogram. $6.90 is $3.45. So the cheapest option is clearly B. Question 18. Andrew, Brandon and Cosmo are the first 3 batters in the school cricket team. In a recent match, Andrew scored 30 runs, Brandon scored 25 runs, and Cosmo scored 40 runs. Part A. What is the ratio of Andrew's to Brandon's to Cosmo's runs scored in simplest form? Okay, so we can make sure we underline that. Now, let's have a look at their runs. Andrew scored 30 runs. Brandon scored 25. So make sure we maintain the correct order. Cosmo, last, scored 40 runs. Now, we can see that all of these terms are divisible by 5 because they end in either a 0 or a 5. So what we're going to do is we're going to divide all terms by 5. So 30 divided by 5 is 6. 25 divided by 5 is 5. And 40 divided by 5 is 8. So there's the simplified ratio. Now part B. In this match, the ratio of the total number of runs scored by Andrew, Brandon and Cosmo to the total number of runs scored by the whole team is 19 to 36. So this 19 here is the term that refers to the runs scored by Andrew, Brandon and Cosmo. So for every 19 runs basically scored by these three players, the whole team has scored 36 runs. So the first thing we need is the total number of runs scored by Andrew, Brandon and Cosmo. So 30 plus 25 plus 40 is equal to 95 runs. So what we want to do is you want to find an equivalent ratio. So 19 to 36 is equivalent to 95. So this is 95 runs, okay, scored by these three players, to X, where X is the total number of runs scored by the whole team. So the way we're going to work this out is by this calculation. 95 divided by 19, then we're going to multiply it by 36. Okay. 95 divided by 19. That tells us how many times 19 goes into 95. And then we're going to multiply that by 36. And we get 180. Therefore, the whole team scored 180 runs. Now, just to make sure that you're on the right track, okay, the ratio 180 to 95, so I'll just do this as a double check, okay. Okay, should equal the ratio 36 to 19. The way we can check that quickly is we enter it in as a fraction. 180 over 95, because fractions and ratios are related, you get 36 to 19. And it works. Question 41. A map is drawn to scale on 1 centimetre grid paper, showing the positions of a supermarket and a cinema. A reservoir is also shown. Part A. It takes 10 minutes to walk in a straight line from the cinema to the supermarket at a constant speed of 3 kilometers per hour. Show that the scale of the map is 1 centimetre equals 100 meters. Now, if you notice, we're working in minutes, go for time, and the scale's in meters. So why don't we convert the speed here, this 3 kilometers per hour, into meters per minute. Okay, so let's do that first. So 3 kilometers per hour is equal to 3,000 meters per 60 minutes. So let's work it out now in meters per minute. Okay. So if we divide both of these terms by 60, okay, 3,000 divided by 60, we end up with 50 meters per minute. Okay, so now it takes 10 minutes to walk in a straight line from cinema to supermarket. So in 10 minutes, distance is equal to 50 meters per minute multiplied by 10, which equals 500 meters. So there are 500 meters between cinema and supermarket. 1, 2, 3, 4, 5 grid squares. equals 500 meters. 1 grid square is equal to 100 meters. 1 grid square is equal to 1 centimeter. Therefore, the scale is 1 centimeter to 100 meters as required. Okay, so we can add that on here. 1 centimeter is 100 meters. Okay, we're going to need that. So let's have a look at part B. The reservoir is initially empty. During a storm, 20 millimeters of rain falls on the reservoir. With the aid of one application of the trapezoidal rule, estimate the amount of water in the reservoir immediately after the storm. Assume that all rain which falls over the reservoir is stored and give your answer in cubic meters. Let's go back to our reservoir. Okay, so trapezoidal rule, we need the two parallel sides of the trapezium. Okay, so what we're doing is we're building a trapezium. Okay, this is 100 meters using our scale. 1, 2, 3. This is 300 meters. Again, using our scale. So that's our scale there. And 1, 2, 3, 4. And the distance between the parallel sides of the trapezium is 400 meters. Okay. So the surface area of the reservoir by the trapezoidal rule is equal to, okay, half multiplied by the distance between the parallel sides. These are the parallel sides basically of the trapezium. If you look at it this way, you can see trapezium. Okay. So half multiplied by 400 multiplied by the sum of the parallel sides, which is 100 plus 300. Okay. And that's equal to, okay, half multiplied by 400 multiplied by 100 plus 300 is 80,000 square meters. So now during a storm, 20 millimeters of rain falls on the reservoir. Okay. So to estimate the amount of water, the first thing we have to do is convert the 20 millimeters into meters. Since the surface area is in meters and we want to answer in cubic meters, that means that the height of water, okay, that's fallen, is the meter equivalent of 20 millimeters. So let's do this. Convert 20 millimeters into meters. Okay, we divide that by 1,000. Okay, if you want to, having a mental blank, just put in your calculator, right? Don't guess your way through this. Make sure you do not lose a mark here. That's 0.02 meters of water that's fallen. So that's going to be the height of water that's fallen. So the volume of water is equal to 80,000 square meters multiplied by the height of water. That's 20 millimeters. Multiplying all that together, and we get 1,600 cubic meters, which is 1,600 kiloliters or 1.6 megaliters. Question 17. Ayla wishes to estimate the number of trees on a square block of land measuring 1,000 meters by 1,000 meters. She counts the number of trees on a 5 meter by 5 meter section of the block and finds there are 8 trees. Based on this, estimate the number of trees on the entire square block of land. So I might just draw a quick diagram here to sort of help you visualize what's happening here. So just imagine, okay, there's our, and sort of it's a very large block of land, of course, but there's our 1,000 meter by 1,000 meter block of land. So the question is, in a 5 meter by 5 meter block or a square, so that's our 5 by 5, we have 8 trees. So the question is, how many of these 5 by 5 blocks of or squares of land are contained within this 1,000 metre by 1,000 metre sort of large block of land. Okay, and we could work that very easily just by using area. Okay, so area of the large block of land is 1,000 by 1,000. We're going to divide that by the area of the small block of land, that's the small square, so this square here. Okay, and that gives us, okay, how many, now I'll break this up into sort of two calculations instead of doing it all in the one. So 1,000 times 1,000 divided by 5, and we get 40,000. So 40,000 of these, okay, of these 5 by 5 sort of small squares will fit in 1,000 metres by 1,000 metres. Okay, that's a square kilometre. That's a very large tract of land. Now, how many trees are there? In a 5 by 5 square, there's 8 trees. So the number of trees is equal to, we've got 40,000 squares of those 5 by 5 metre squares. Each one has 8 trees in it. So the estimate, therefore, now I should say more accurately that it's the number of trees is really an estimate. Okay. So 40,000 times 8, and it's 320,000 trees estimated. Question 23. In a tropical drink, the ratio of pineapple juice to mango juice to orange juice is 15 to 9 to 4. Part A. How much orange juice is needed if the tropical drink is to contain 3 litres of pineapple juice? So let's go back to the original ratio. So these terms of the ratio correspond to the pineapple juice, mango juice, and orange juice respectively. So I'm just going to put just a letter there just to indicate sort of what the term corresponds to. So the P is pineapple juice. The term here, the 9, corresponds to mango juice, so I'll put an M there. And orange juice, I'm just going to put the O there next to the 4. So 15 to 9 to 4, so that's our original ratio. We have the amount of pineapple juice, so in this drink, so we do know that we have 3 litres, but we want to know how much orange juice is required, so that's the O, that's this 4 here. So what we want is the equivalent ratio. 3 litres of pineapple juice, so many litres of mango juice, we don't know what that is at this point, to orange juice. Now, I might actually just put an OR so we don't get confused, that's not a 0. Okay, so it doesn't make sense if it is a 0, so that's OR, so for orange juice there. So we want to try and find the amount of orange juice, given that we have 3 litres of pineapple juice. Now, if the original term of the ratio that corresponds to pineapple juice is 15, but the equivalent ratio, it's a 3, what do we divide the 15 by to get 3? And it's 5. So we're going to divide basically every term of this ratio by 5 to get the equivalent ratio. Okay, so now we're not interested in the mango juice, we only want the orange juice. Okay, so 4 divided by 5 gives us the amount of orange juice. Okay, and 4 divided by 5 should give us 0.8. Okay, or 800 millilitres. Okay, either way, they're both correct. Okay, since the original unit of measure there is litres, we should be answering in litres and just keep it in litres. Okay, so I'm going to just remove this last answer there. Okay, so I think it's very important that we keep the answer in the original unit of measure there. Let's have a look at part B. The internal dimensions of a drink container in the shape of a rectangular prism are shown. To completely fill the container with the tropical drink, how many litres of mango juice are required? So I think the first thing we need to work out here is what's the volume of this container. So maybe we'll work that out first. Okay, and it's a rectangular prism, so we just multiply all the dimensions. So 40 times 20 times 35 centimeters. So 40 times 20 times 35, and we get 28,000. That's cubic centimeters, so that's equal to 28,000 milliliters, which is equal to 28 litres. So that's 28 litres in total. Okay. Now let's go back to our original ratio. So this is the ratio, this is the 15 to 9 to 4. So the total number of parts, okay, is equal to 15 plus 9 plus 4. Okay, so it's 15 plus 13, that's equal to, there's 28 parts. Okay. Now that's quite convenient because it's 28 litres, okay, and there's 28 parts in the ratio. So the value of one part, or one share, is 1 litre. So going back to the original ratio again, the 9 represents the amount of mango juice. So there are 9 parts of mango juice. Okay, so 9 times 1 is equal to 9 litres, therefore 9 litres of mango juice is required. Question 27. The shaded region on the diagram represents a garden. The scale is 1 centimetre equals 5 metres. Part A. Use 2 applications of the trapezoidal rule to calculate the approximate area of the garden. So the trapezoidal rule means we're going to try to estimate this irregular area by drawing trapeziums basically around it. And we need 2 applications, which means 2 trapeziums. So the trapeziums have to be equal height. So what we're going to do first is I'm just going to draw it in lightly. Okay, the first trapezium. So this is the first trapezium there. And then we're going to draw in the second trapezium. Now the second trapezium actually doesn't actually look like a trapezium. It looks like a rectangle, in fact. Here we go. So the 2 trapeziums have equal height. Now the scale is 1 centimetre equals 5 metres. So let's confirm this. Okay, so each of these squares is 1 centimetre. Okay, so there's the halfway mark there. So this is of the length of the rectangle. So 5, 10, 15, 20. So the height of the trapezium, or each trapezium, is 20 metres. Now let's work out the side lengths of this trapezium, or the length of the parallel sides. So 1, 2, 3, 4, 5. So that's going to be 25 metres. Okay, 1, 2, 3, 4. So the common side between the 2 trapeziums is 20 metres, and this one's going to be 20 metres as well. Okay. So now let's apply the trapezoidal rule. So the area of the garden is approximately equal to the area of the first trapezium. So we can see that the trapezium in fact overestimates the area of the garden. But that doesn't matter. That's going to feed forward into part B. So we'll get to that shortly. Okay, so the first trapezium, okay, it's half the height. So it's half times 20 times the sum of the parallel sides. So that's going to be 25 metres plus 20 metres. So that's the first trapezium plus the second trapezium. Now the second trapezium happens to be a rectangle. So you can either use the trapezoidal rule, or the area of a trapezium, or just the area of a rectangle, 20 times 20 meters. But let's just use a trapezoidal rule for consistency here. So half times 20 times the sum of the parallel sides. So it's going to be 20 plus 20. Okay. And entering in all of that. Okay, so we get half times 20 times 25 plus 20. Okay, and I can enter this all as one calculation, or you can work out each trapezium one at a time. Okay, and then just add them together at the end. Plus half times 20 times 20 plus 20. And we get 850 square meters. Now, part B. Should the answer to part A be more than, equal to, or less than the actual area of the garden? Referring to the diagram above, briefly explain your answer. So the answer to part A, we can see that the trapezium overestimates. Okay, so there's some area here that it includes, which is not actually part of the garden itself. Okay, so it'll be more than. Okay. More than the actual area, okay, of the garden. As the shaded area, or the shaded region, is less than the area of the trapeziums drawn in the diagram above. Okay.